Hello, everybody. Today we're going to learn about bodies of water and how they can potentially affect climate. Before we get into their effects on climate, we got to talk about just bodies of water in general, and oceans are a good place to start. They're the biggest bodies of water in the world, and ocean currents are very, very important to how these bodies of water function and how they work. So, ocean currents move in one direction logically, and then the other direction maybe, or not intuitively, I should say. Uh, Horizontally, it makes a lot of sense. Currents we always think of as moving across the globe, right? But they also move up and down, and there's circulation between these movements as well. Sometimes horizontal currents will fall into vertical currents and vice versa. And ocean currents are affected by gravity, wind, Coriolis effect, water density, and a bunch of other stuff. Oh, I think I didn't put it in there, like the position of continents and land masses. Oh no, I just put it on this slide. So these are all the things that affect um, currents and how they function and how they work. So I'm going to go over a couple of these. I'm not going to go over gravity because I think that's fairly intuitive. You guys know that gravity will pull water down. Um, but let's start with a certain type of wind called prevailing winds. So prevailing winds are winds that tend to exist all the time, where it's like the average, I suppose. And oh, excuse me. And these winds, because they're always there, are affecting the top level of that water and creating forces on that water and creating currents. So you notice in the kind of the northern hemisphere, you've got these kind of winds going across here to the east, right, coming from the west. And you've actually got that in the southern hemisphere as well. And then in the equator, you've kind of got them prevailing in the other direction, coming from the east. And sometimes you'll hear these called trade winds, stuff like that. And I mentioned the Coriolis effect up here. The Coriolis effect is a really interesting thing. It's the force that is exerted on things on the Earth because of the rotation of the Earth. And a lot of the time we think like, oh, how come we don't just like fly off the Earth? Or we think, how come I can't feel the Earth spinning? And even though you can't feel it, you can see the effects of it through a lot of different things. And ocean currents are one of them. The really interesting thing about the Coriolis effect is at the top of the Earth, since the Earth is a sphere, at the poles, stuff up there is moving, it'll rotate from one spot all the way around the next spot. But if you're in the center in the equator, you're going to rotate in the same amount of time a much further distance, which means stuff in the center of the Earth or along the equator, the closer you are to the equator, you're actually moving more quickly than you are when you're at the poles. So this can create some pretty bizarre forces, and a lot of these forces will affect kind of how ocean currents work. Ooh, let's talk about water density. So water density, I think, is something I learned this in university for the first time. I'm going to tell you guys about it though, because I think it's cool. We won't go too far into it. You can look into it more if you want, independently. But I think it's a really neat thing. So when anything heats up or cools down, it changes density. We learned this with water turning into ice, and it changes its density so it floats, right? And some water might be heated, like the thing, think like the water near the top of the water column, right? If you're swimming in a lake, the very top layer is really nice and warm. And some water might be cool. So if you go into the ocean and you go 1,000 meters down, that water is going to get cold because none of the sun is reaching there. And this can create something called thermoclines. You can even have thermoclines that are not extremely deep. They don't take a ton of water. But thermoclines is, or a thermocline is a really cool phenomena where water of two different temperatures will not mix because they have different densities, and it creates this like line in the water, or this like zone in the water where you've got the surface layer of water, which is like pretty warm, especially up at the top, and then you hit this thermocline where there's like a little bit of mixing, but not really, and then below that you've got this like really cold water, and this surface layer and this deep water will not mix. it takes a ton of kind of turbulence to mix these things up. And naturally, that's not going to happen. There's an experiment we did in university where we took a fish tank of water and we took a blow dryer, turned it on hot, and kind of blew it along the surface of the fish tank, and it heated the top level of the water to quite warm. And then we drop in food coloring, and you'll notice the food coloring hits all that warm water, spreads throughout it, and then stops. Like there's this like distinct line where it just doesn't drop into the bottom water because there's a thermocline that we've created, right? All the hot water isn't going to mix with all that cold water down there. And it was a very cool thing. It looked almost like reality had broken because you expect that water to drop and like mix through the whole, or sorry, you expect the food coloring to drop and mix through all the water. But that top level, it just like it was like it hit a brick wall when when it went into the water. So this is very important for how currents might behave, and the idea that there are surface currents and deep currents as well. There are currents um, heavily affected by the temperature of the water, and sometimes it defines why they move the way they do. Another example of kind of thermoclines that you might see on a smaller scale is think about cold spots in the water if you've ever been swimming in a lake, or really warm spots, right? Oftentimes you'll find pockets of cold water, and the reason water isn't just totally uniform in temperature is partially because the water density. That cold water doesn't want to mix with the warmer water, so it stays together. It's kind of cool. Okay, so ocean currents. Uh, you're you're not gonna have to memorize this. I'm kind of just putting this up here for illustrative purposes. There's a lot of them, um, and you'll notice the trend on a couple of these, right? Is the currents kind of on the north hemisphere kind of all go towards the right a little bit. Currents in the middle kind of go to the left, and then currents on the southern hemisphere kind of go to the right. And that mirrors very closely what we see here. We see the trade winds, the prevailing winds going to the right on both the poles and to the left in the equator. So obviously there's some variation because you'll notice like these circular currents in here, these are probably heavily affected by all of the land masses that they're hitting up against, right? You can see, or you can imagine the prevailing winds pushing the equatorial water this way, and then it hits the coast of Africa and it starts spinning around, and then it gets caught in the southern hemisphere winds and it starts curling back over here and it hits Australia and kicks back up in here, gets pushed. So you can notice these swirls are caused by a mixture of these traits that affect this kind of stuff. And this is a really excellent picture of an ocean current that exists, and there's like transfer of water between all of these oceans through currents. But the red is what happens on the surface. And then you'll notice up here and over here and right here, there's a transition where it would actually, this would be surface water and it would drop, and it would be the water would cool down, drop in the water column, and then flow under the surface and in the opposite direction. So the density of these currents makes them basically go in opposite direction, or there's currents going in the opposite direction, and the density keeps them separate because one of them is this warm water and one of them is this cool water. So you'll notice this stuff here. This is probably talking about surface flows in general, um, but there is a like kind of a whole nother level of ocean currents that are occurring deeper down. They don't necessarily match what's happening on the surface. So the big question that we have for this chapter is, how do bodies of water affect climate? And we kind of already talked about this. We talked about the concept of a heat sink or a heat source just a little bit. I'm going to elaborate on it here. So generally, large bodies of water are going to moderate the climate. You'll have noticed this if you pay attention to like Winnipeg's temperatures versus Vancouver's temperatures. Vancouver's temperatures go from, actually, I'm not really sure what they go from. just below freezing to 20, 25 maybe in the summer. And that kind of thing is going to be pretty average, right? They're going to have spikes that go below and above that. But if you look at Winnipeg, this last couple of weeks is a good example. We went from 8 degrees to 28 degrees in the course of a couple of days. And our temperature range, I think, is about 50 degrees Celsius on average. So minus 25 to positive 25 from winter to summer, which is pretty nuts. There's not many places in the world that have such a wide range. I think there's quite a few places in Russia and then Winnipeg, and it's because those places are in the center of continents. So you'll notice the places that have large bodies of water beside them don't have these large temperature ranges. And because of the high heat capacity of water, water can take up a lot of heat and give off a lot of heat. So in winter, large bodies of water will give off heat because they'll have a bunch stored up. And since the surrounding area gets really cold, they'll give off heat. This is called being a heat source, right? You've got the temperature of the water much higher than the temperature of the land. So this is going to give off heat. And a heat sink is over here. In the summer, large bodies of water are going to take up heat because they're going to be cold from over the winter. The land and the sun's going to hit the land and warm it up, and the air is going to get really warm. So it's going to start absorbing heat, which means in the summer in Vancouver, it's going to be a little cooler. And in the winter, it'll be a little warmer because you've got this big body of water giving off all this heat. So that's the idea of the heat sink and a heat source with a little more detail. This is tightly tied into the heat capacity of water, which we talked about last time. So hopefully that makes a bit of sense to you guys. Cheers.